Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. And you might be wondering, why are we talking about this particular form of energy flux with relation to the thermal conductivity? We talked about this on our previous video where we saw different relationships and different outcomes when it comes to interpreting this particular big formula, where you not only determine the coefficient of thermal conductivity but also how this will make an impact in various relationships with its conditions, with pressures, and also with that of the specific heat capacity of a specific gas. So in this particular video here, we're going to be looking at a particular example where we're asked to calculate the thermal conductivity of nitrogen at 300 kelvins at 15 millibars. Each gas is confined in a cubic vessel of size 15 centimeters, one wall being at 305 kelvins and the opposite is at 295 kelvins. Now the other question is, what is the rate of flow of energy from one wall to the other in each case? Now take note first that in this part we're asked to first calculate the specific thermal conductivity. So in our givens, in this question we're given the temperature, which is 300 kelvins. We don't have to convert it from degrees Celsius to kelvins like other examples on our previous videos, but also you're given the in 15 millibars, and in here we know that milli is in this case 10 to the power of -3, and this is in bars. We need to convert this to pascals, and to do that we know that 1 bar is equal to 10 to the power of 5 pascals. Therefore 15 times 10 to the power of -3 multiplied by 10 to the power of 5 pascals will enable us to determine our pascals. Therefore, by evaluating the powers, we have product. Therefore, converting product, we'll keep the base and we add the exponents. In this case, -3 plus 5 gives us +2. Therefore, we have our new pressure now in terms of pascals to be 15 times 10 to the power of 2 pascals. And so once you have this, the other one is the heat capacity of our specific molecule, which in this case is nitrogen gas. Take note that the heat capacity of this particular system has to be done at constant volume. So therefore our heat capacity of nitrogen, when you look at it on the table, is around 20.6. in this case is measured in joules per kelvins per mole. And so once we have this taken care of, our next one is to be able to look at the specific R, which is our constant. Which are the possible constants we're going to come up with or come across? And we know that R is a gas constant, which is in this case 8.314. Take note that this is measured in joules per mole per Kelvin. And the next one here is looking at the K value, which is our Boltzmann's constant, which will be a potential constant that will be used in this example. And next is possibly the molar mass of our specific nitrogen gas, and we know that for one nitrogen atom is 14.01. This time it is going to be multiplied by 2, which is 28.02. And take note that the unit is in grams per mole. We need to convert it to kilograms per mole. Therefore we are going to multiply that by 10 to the power of -3, and therefore you have 28.02 times 10 to the power of -3. Take note that this is measured in kilograms per mole. So next is finally going to a particular table to figure out what the specific cross section of our nitrogen gas is. So once we have this taken care of, the next question is based on the question, which asks us to first calculate the thermal conductivity. And so in this case here, our required is to be able to figure out the thermal conductivity, and based on our previous video, thermal conductivity is shown to be in terms of K, which is in this case the coefficient of thermal conductivity. And so that bk is what we are going to figure out. Our analysis based on this is going to be able to derive a formula that fits the specific givens, and being able to do that involves the following. First, we know that our k, based on our previous videos, is equal to 1/3 of the mean free path multiplied by our mean speed, and this is multiplied by the heat capacity at constant volume of our specific gas, and this is multiplied by the molar concentration of our gas. Now this is also expressed as C, which is the mean speed multiplied by the heat capacity at constant volume, or divided by the 3 square root of 2 multiplied by our specific cross-sectional area multiplied by the number of particles, in this case number of nitrogen gases. Now we need to look at these two equations that expresses k and figure out which one is closely or will be important in fitting our givens here. What we see here is that the given doesn't show the concentration of our specific nitrogen gas in that particular cubic space. Therefore, we're not going to use this. We're going to use this one right here, so that we will be able to just only transform our number of particles here to something more favorable. Like for example, in here where we know that our specific relationship with the number of particles is actually conditioned to be connected to the gas constant divided by the specific Boltzmann's constant, and also we know that our C bar, which is the mean speed, is equal to the square root of 8 multiplied by RT, or divided by pi multiplied by the molar mass of our gas. And once we have these two expressions here, one involving our N, we can replace that with R over T in this equation. And for our C, which we're not given the question, we can now replace it with RT, which are given, and also M, which is the molar mass in this equation right here. And so therefore, as a result, we'll be able to come up with our new expression for our K to be now shown as the following. We have our new K, which is, take note, this K is the thermal conductivity constant, to be equal to the mean speed, which we've not actually put its new expression yet, is equal to C, which is the mean speed multiplied by the heat capacity of our gas multiplied by, take note that this K is represented as the Boltzmann's constant, or divided by 3 square root of 2 and multiplied by our specific cross section of our gas multiplied by our gas constant. So once we have this, the final step is to replace our particular mean speed with this equation, and what we have is now showing a new equation that we're going to put our solution or our givens in. We're going to put in our givens as shown here, or green, in this particular equation. And so therefore we have this to be showing not only the specific values, which are the constants, but also the units, so that we're going to evaluate our units properly. So first, in the square root, we have, now on the other hand here, we're dealing with, so that is how to express this, and therefore we'll be able to evaluate first our specific units. And to evaluate our units, we're going to cancel some things out, which are as follows. We have our kilograms cancelling out our kilograms, we have our kelvins cancelling out our kelvins, we have our mole cancelling out our mole, and we're left with in the square root meter squared per second squared. And on the other hand, in the brackets, which is focusing on these regions, we have a couple of things that are related. We have our kilograms cancelling out kilograms, and we have our seconds cancelling out our seconds here, and we have our kelvins cancelling out our kelvins, we have our mole, which cancels out our mole, and we have our meter squared cancelling out our meter squared. And this is one of the things that I will notice here. We have our meter squared cancelling out our meter squared. We're good with this. So therefore, our K, which is our specific thermal conductivity constant, is equal to all square root of our constant, which when you multiply all these numbers here and divide it by the numbers here, we actually come up with, don't forget there's a bracket here, we have, and then in the new bracket here we have these particular constants are multiplied, and we have and divided by the ones at the bottom here. And what we have is our next step here is to be able to deal with the specific constants and also eliminate our square. And this for our thermal conductivity shows that our meters squares will cancel and we will left with the elimination of our square roots, and the squares applied to our specific number here, and that gives us in this case a number, and that number is going to be multiplied by this particular number right here. And take note that in this case we're going to have our meter going to be multiplied by our kilograms, and our seconds will be multiplied by our seconds squared times Kelvin. And so what we have is our number, which is our constant, to be equal to, take note this is measured in kilograms, meter per seconds cubed multiplied by our kelvins. And so this is actually interesting because when you rearrange some things here, you'll be able to get a true new derived unit based on what we see here in terms of joules. And what we notice is that first, to derive joules, we notice that kilograms meters squared per second squared is equal to joules. So when you multiply both sides by a specific constant, which is 1 over m, we actually have kilograms meters squared is cancelled out, so we have what is left is 1 meter, and this is per second squared is equal to joules per meter. And so therefore, where we see in this case kilograms meter per second here, we actually put joules per meter. And so therefore we have our new expression for our specific thermal conductivity to match the unit conversion, which is, this is the answer for the thermal conductivity of nitrogen gas at that particular temperature. And in this case we are given a specific pressure. And so the other question in here is related to what is the rate of flow of energy from one wall to the other in each case. So take note here that in this part we have one wall temperature on one side to be in this case measured as T1, and T1 is measured 305 kelvins, and the second wall here, which is the other end, temperature is dropping and it results in 295 kelvins. And so we know that the cubic vessel has a specific length, or the particles travels from here, which is T1 to T2 at a distance of around 15 centimeters, which is around roughly 15 times 10 to the power of -2 meters. And so the question here is asking what is the rate of flow of energy from one part to the other. So what we need to think about is, what is rate of flow of energy? Rate of flow of energy, which is going to be expressed as rate of energy flow, is considered to be equal to, in this case we have our K value, and we know that the K value is negative always based on what we derived from our equation right here. It shows a negative value for our K, and so therefore in this part here is equal to negative our thermal conductivity, and this is going to be multiplied based on looking at the unit. We know that the rate will have to be shown as energy, in this case per second. So therefore based on this we need to somehow adjust our specific K value in such a way that we're going to deal with the unit by eliminating some of the units by doing the opposite of the operation. So therefore we're going to be multiplying our thermal conductivity by our temperature change, and this will be multiplied by our distance, which is what is taken or what it takes for our particles to go from or transfer the energy from T1 to the other end, T2. So therefore, we have our resulting expression. Our thermal conductivity is, in this case, approximately, we're going to multiply by our change in temperature, which shows that our initial temperature will be subtracted from the final temperature. We have the other part which we're going to multiply, which is the length, which in this case is 15 times 10 to the negative 2 meters. And so in this case, we're able to eliminate some of these variables. Units, in this case is meters, cancel out our meters, and our kelvins cancels out our kelvins. And what we have in this case is negative signs canceling out. Where you perform your subtraction here, we get a negative value, negative cancels out our negative, and therefore we'll be able to determine our specific rate of energy flow, or the energy gradient in this case at a specific time, to be equal to 0.0135. Take note that this is measured in joules per second. So those are the two answers that we're able to determine based on this particular question right here. Thanks for following me through this. Truly appreciate it. Please hit a comment down below. Let me hear your thoughts about this, and also whether you found the unit conversion or derivation really a fun way to see and to confirm that the answer that you have here, which is in this case in joules meter per meter per second per Kelvin, actually matches our specific previous video unit for our K, which is what we have right here. So see you on the next video. Stay smart as always, and believe in yourselves.